Exponential functions. They're the rock stars of the math world, always increasing dramatically or falling off pretty much just as dramatically. Today I'm going to teach you what they are and how you can use them to help you make money. Real quick, we're going to go over some prerequisite knowledge that you have to understand exponential functions. The first thing we need to know about is algebraic expressions. And as a reminder, algebraic expressions are made up of broadly three different types of thing. Operations. These are things like addition, subtraction, multiplication, and division. But it's also things like equalities, inequalities, square roots, grouping symbols, or exponents. Constants are exactly what they sound like. Constants do not change, and these are numbers. But these aren't just your everyday counting numbers sometimes. Sometimes they are. Sometimes they could be like 1 or -3. But sometimes we have some more creative numbers, like our favorite and most delicious number, pi. We could have decimals, like 2.75, fractions, for instance, 7/2, and even more esoteric numbers like e. More on that one later. Finally, we have variables. Broadly speaking, variables are letters, except when they're not, looking at you, E, but letters that we use to represent unknown quantities. More often than not, these are X, Y, A, B, and pretty much any other English lexicon letter that's not already used to describe something else. The other thing we need to know about is the concept of a function. Now, a function is basically just a machine that takes an input, does something to it, and turns it into an output. The most commonly used variables for inputs and outputs are, of course, x and y. And a function gives us the rule that turns an input into an output. So, for example, if our function was y equals 2x plus 1, and our input was 3, we would take our input and input it into the function. And then we would evaluate that function according to the order of operations. We would do 3 times 2, 6, plus 1, would give us our output, y equals 7. Very important that this is according to order of operations. So what is an exponential function? An exponential function looks like either of these two forms. Of course, one is in y form, one is in function notation. Y equals a times b to the power of x. You'll notice that the input this time is in the exponent. That's why these are called exponential functions. Our input is actually in the exponent itself. A, in this case, is the starting value of the function. Oftentimes, this is derived from the context of the problem because exponential functions have very real, practical applications to real life problems. B is what we call our base. The base is what's being raised to the exponent where our input is. So if we look at an example function over here, f of x equals 3 times 2 to the power of x, Let's evaluate a couple of these and see what the outputs look like. If we plug in 0 for our input, then that's 3 times 2 to the power of 0. And according to the rules of exponents, anything to the 0 power is 1, and 2 to the 0 is 1. 1 times 3 would be 3. Keep it going in the same way. If we plug in 1, this is 3 times 2 to the first power. 2 to the first power is just itself, leaving us with 3 times 2, which is, of course, 6. Now, this is where things start to get interesting. 3 times 2 to the second power. Well, 2 to the second power, that's 2 times 2. So we have 3 times 2 times 2. 3 times 2 is 6. 6 times 2 is 12. And I'm hoping you can start to see the pattern here. Every time we go up 1 in the exponent here, we're going to add another 2 to the end of this chain of factors. 12 times another 2 would give us 24. 24 times another 2 would give us 48. And 48 times another 2 would be 96. Now, this is a pretty dramatic increase across only an increase in 5 to our input. We went from an increase of a total of 5 in our input to an increase of 93 in our output. And this is one of the main characteristics of exponential functions. They grow or decay very, very rapidly. So let's look at a graph of f of x equals 3 times 2 to the power of x. And here we have a graph. This is in Desmos graphing calculator. And if we can see over here, this is the same function, f of x equals 3 times 2 to the power of x, and we've included a table here. If we go up one more input, we are already at 192 as our output. And we see that if we zoom out, this graph just gets steeper and steeper. And that is one of the main characteristics, again, of exponential functions. Possibly the most important aspect of exponential functions is the base, b. The base, again, is the number that's being raised to the exponent. The base b determines how fast the function grows or decays. An exponential function grows when b is greater than 1. Any real number greater than 1. So, for instance, 2. 2 is greater than 1. That would mean your function is doubling every time you go up by 1 in the input. Another example of something greater than 1, 1.05. It's 0.05 greater than 1, so it is an exponential growth, but not nearly as fast as a base of 2. An important note about bases is it does not matter how you write them as long as they are mathematically equivalent. 1.05 is the same thing as 1 plus 0.05. And a lot of times we prefer this representation because it helps us more easily identify the rate at which an exponential function is increasing or decreasing. We can see that this exponential function would be increasing at a rate of 0.05, expressed as a percentage, that is 5%. A rate of 5% per one increase in the input. An exponential function decays when b is between 0 and 1. This is when we have fractions that are less than 1, and decimals that are, of course, between 0 and 1. So we can have things like 0.75 or 1/4. Of course, 1/4 is the same thing as 0.25. Again, if they are mathematically equivalent, feel free to substitute whichever form you like. It's important to note that exponential functions cannot have a negative base or a base equal to 1. And I'll show you why it cannot be equal to 1 in just a second. So let's look at a graph that looks at different bases and how they affect the resulting graph. Now we've zoomed out on this graph a little bit, but right now this graph is the exact same one as example 1. A is 3, B is 2, gives us 3 times 2 to the power of x. As we start increasing our base, you can see what happens to the graph as it starts getting steeper and steeper. And these are only changes by 0.1 of the base. So you can imagine how dramatic the change would be if we increased the base by, say, 100. Going back down here, we stop where we were for example 1. As we get closer and closer to 1, you can see that our graph starts leveling out quite a bit. It's not increasing as quickly the closer we get to 1, but it is still increasing. Now, one of our caveats that we said was that b could not equal 1. Well, why couldn't b equal 1? Let's look. That is a horizontal line, and it occurs because if this base is 1, then 1 to any power stays the same. 1 to the first power is 1. 1 to the second power is 1. So, it's always going to be 1 times a. So in this case, it's going to be y equals 3. Always, no matter what the input is. So that's why exponential functions cannot equal, the base of exponential functions cannot equal 1. And that's because, well, it wouldn't be exponential. This is what we call a linear function. Now, if we reduce our base to less than 1, between 0 and 1, we can see that suddenly our graph has flipped. No longer are we going up, we're going down as we go to the right. And as we get closer and closer to 0, you can see that the graph gets steeper and steeper and steeper the farther we go to the left. As b approaches 0, this thing will get infinitely steep, and this graph will decay very, very, very quickly. So let's look at some real-world examples real quick. Imagine a population of rabbits that doubles every year. Starting with 10 rabbits, how many will there be in 3 years? So it's always useful to write down our general formula when we are confronted with word problems like this. F of x equals a times b to the power of x. And we have to remember that a is our starting value and b is our base. Now, how you set up problems like these is we always start with our starting value. In this case, that's 10 rabbits. So we'll start with f of x equals 10. And we know that inside these parentheses needs to be our base. And our base has something to do with the rate at which the population increases. The population doubles every year. That means that every year we're going to have 100% of the population, and we're going to add an additional 100% of the population. Of course, this is 100% expressed as a decimal, which is, of course, just 1. And we raise that to the x power. Now, you can simplify this to get f of x equals 10 times 2 to the power of x. Or you can keep it as 1 plus 1 to show that you are adding 100% of the previous population every year. How many rabbits will there be in 3 years? Well, 3 in this case is our input. So f of 3 would be 10 times 2 to the third power. 2 to the third power is 2 times 2 times 2. Gives us 10 times 8. So, in 3 years, the population of 10 rabbits has exploded to a population of 80 rabbits. Now, you might ask, is this exponential growth or decay? Well, the outputs are increasing, and our base, as you can see, is greater than 1, so it is exponential growth. Something we can double check by looking at a graph. Our initial value was 10, our base was 2, and our power was x, and as you can see, this graph increases very, very dramatically. And that we actually have to zoom out this far to locate f of 3, which is right here. F of 3 being the population of rabbits after 3 years, 80. Now, you could use a graph like this to predict the population after any number of years that you would want to know. If you wanted to know the population after 10 years, we can simply type in f of 10. And after 10 years, this population of 10 rabbits has increased all the way to 10,240. This is why we use rabbits as a very common example of exponential growth. They breed very quickly, so they can very quickly take over an area if not properly controlled. Another example is radioactive substances. A radioactive substance halves its quantity every 5 years. Now this one, when we plug it into our formula, it's going to require a little bit of tweaking, but that's okay. I'll show you how to do it. Starting with 100 grams, how much will remain after 10 years? So we start with our base formula, f of x equals a times b to the power of x. And we start with our starting value. F of x is equal to, well, we start with 100 grams. As for the rate, it tells us that the substance halves its quantity. Well, as a rate, that would be 100% minus, well, half of 100% is 50%. We are subtracting 50% of the population every period of time. But that period of time is in years. But it halves its population every 5 years. So if our x is in years, then in the exponent, we have to account for the fact that it doesn't reach half of its original substance until 5 years. So we divide x by 5. And we get 1 minus 0.5 to the x divided by 5. In this way, once we hit x equals 5 years, 5 divided by 5 is 1. And our base is 1 minus 0.5. 50%. 50% of 100 would leave us with 50 grams of the substance after 5 years. Well, that's not what it asks us, though. It asks us how much will remain after 10 years. So we plug in f of 10. F of 10 is 100. And we can simplify this. 1 minus 0.5 is 0.5. 50% to the 10 over 5. Well, this is 100 times 0.5. 10 divided by 5 is 2, which is 100 times 0.5 times 0.5 is 0.25. And 100 times 0.25 gives us 25 grams. So in only 10 years, this radioactive substance has decayed from 100 grams to 25 grams. Again, let's look at a graph. This was our starting value, 100 grams, at 0 years since the beginning of the experiment. You can see after 10 years, the amount of radioactive material has decreased dramatically. And we can even look on our graph if we wanted to find out in 100 years how much of the substance remained. Now, Desmos is telling me that 0 grams of the substance remain after 100 years. Now, this is due to a limitation of the computational power of a calculator. In reality, this will get closer and closer and closer to the x-axis, but never actually touch it. Let's use a smaller number that Desmos might be able to handle a little more easily, like 50. As you can see, 50 years later, we have 0.098 grams of the substance left. Where we started with 100 grams, 50 years later, we have a little over 9/100ths of a gram of that substance left. And let's look at one more real-world example here. Let's say you put $1,000 in a bank account with an annual interest rate of 5% compounded annually. How much money will you have in 10 years? Compounded annually is a very important term when we're talking about exponential functions, because compound interest is based upon the mathematics of exponential functions, exponential growth or exponential decay. So we can use this formula up here, which is basically just our original exponential function formula, but using a couple different variables. In this case, A is your money after T years. In this case, P is your starting amount of money. R is your interest rate. n is the number of times you compound per year. And of course, t is time. This is measured in years. So if we take the different aspects of this example and plug them into our function, well, we want to know A. So A equals our starting amount, $1,000. We're going to multiply that by 1 plus our rate. Of course, we're going to express the rate as a decimal. So you divide 5 by 100 and we get 0.05. It's only compounded annually, so 1 time per year. So we're going to raise that to the 1 times t. Now this looks complicated, but 0.05 over 1 is just 0.05. So simplifying a little bit, we get A equals 1,000 times 1.05 to the power of t. And to find out how much money you'll have in 10 years, we just plug in 10 for t, 1.05 to the 10th power. And plugging that in, you end up with about $1,628 and rounding up about 90 cents. Not a lottery win by any means, but enough to afford a decent math conference, maybe a trip to Comic-Con, or maybe the next-gen console everyone's looking for. Let's look at a graph. We can see that in year 0, we start with that $1,000 that we put in, and in year 10, $1,628.89.5. Of course, we round that up to 90 cents, unless you're a gas station. So these functions aren't just for theoretical fun. They model real-world scenarios, from bacterial growth in a petri dish to your slowly depreciating car. So that's the lowdown on exponential functions, whether they grow or whether they decay. Remember, in the world of exponentials, what goes up does not necessarily come back down. If you enjoyed this overview of exponential functions, hit subscribe for more. If you have questions, thoughts, or existential math crises, please drop them down in the comments. See you next time.